Good evening to all the participants. I would like to thank Prof. Nawaz, who is been with me since from first webinar, and he is giving me the opportunity even without missing even one webinar also. This is the 10th presentation of mine. Basically, I'm a mathematician. I work in Gulbarga University, which is situated in the south of India. And my name is JC Umavathi. I have experience of more than 35 years in teaching, and I guided nearly 15 students for doctoral, and also I did my postdoctorate in Italy. My basic field of research is fluid mechanics. So, I am not an expertise in experiments. Mine is completely based on modeling, mathematical modeling. And here we are going to study the heat mass transfer. My main motto is to understand the heat mass transfer of fluids flowing through different geometries. My actual expertise is in building in-house codes, especially for multi-fluid flows. I have succeededly done my in-house codes and published a lot of papers. To my account, I have nearly 270 papers. I just want to point out that expertization is in coding. So for that, I consider different types of fluids. As we know, the present era is depending on most of the research work is depending on nanofluids. So I thought let me try what is the outcome of these modelings through mathematical modeling only, and we are going to analyze it numerically. So rather than taking regular Newtonian fluid, because Newtonian fluid we find a lot of literature, and also the Newtonian fluids are applicable only in furnaces or heat exchangers like that. But apart from Newtonian fluids, as we know that there are a lot of non-Newtonian fluids. Again, in non-Newtonian fluids, we know very well that you don't have a particular format like how we define a Newtonian fluid. Yes, this is the Navier-Stokes equation for Newtonian fluid. We know exact relation between stress and strain because it is a linear relationship. So Newtonian fluids, we have a very good formulation. But whereas for non-Newtonian fluids, because it is a non-linear relationship between stress and strain. So non-linear, the word non-linear itself implies that it is unknown for us. So what we are going to do is, depending on some of the experimental results, we are implementing those experimental results and do the modeling mathematically. And after that, we are going to compare this model with the experimental results. So in that case, we are going to define some good relations between stress and strain. This is how the fluids are generated, non-Newtonian fluids. I don't deny that whatever the non-Newtonian fluids that exist that we are going to study are limited. No, anybody can have their own non-Newtonian fluid, but only the thing is one should be very confident that the relation between stress and strain, that non-linear relation, should match with any of the existing fluids. Because after all, research is nothing but for application. Whatever research we do, it should be applied. Then only it has some meaning. So in that perspective, we see that way back in 1966, Eddingen, a pioneer work in non-Newtonian fluids. Everybody should read that paper, Micropolar Eddingen, 1966. He has developed a fluid and he named that fluid as a micropolar fluid. And in that paper, he has very clearly given all the, from the basics, the stress and strain relationships. Not only that, why I am much fascinated with this fluid is because from micropolar fluid, we can go for here micropolar. The word itself will tell that micro, that means it is small. Polar, that means you have polarization. Fluid, of course. Here, whenever you go for micropolar fluid, it has the rotation. It has the rotation. So, depending upon the clockwise and anti-clockwise rotations, we have the particles wherein we have to include the rotational effects also. Apart from the, in Newtonian fluids, we don't consider all this. We just assume that it's again, Newtonian fluid is again based on the, all fluids is based on modelings. And of course, it is created with the experimental validation. No fluid is 100% validated with the experiment. That is damn sure. So you cannot tell that, yes, air is a fluid that matches exactly with this Navier-Stokes equation. No, there is a percentage of error is always bound to happen, because whenever we go for modeling, we cannot exactly match with the experimental results. However, it's enough if we get 90% or 95% accuracy with our experimental validation. So Eringin developed this, wherein he incorporated rotational effects also, apart from the linear momentum of the particles. Apart from the microrotational effects, again, we can extract with the micropolar one more fluid, what we call it as a coupled stress fluid. So coupled stress fluid becomes a part of micropolar fluid. In coupled stress fluid, we include coupling effect also. And I have published a paper way back in Canadian Journal of Physics that considering blood as a model of coupled stress fluid, I got very good validation with the experimental results. Even Eringin quotes in his paper the micropolar fluid in the absence of rotational effect, considering only coupling effect, we can get one more fluid. But however, people also tried to model this micropolar fluid with respect to blood. So there is an ambiguity. There is an ambiguity whether to consider micropolar fluid as a model for blood or coupled stress fluid as a model for blood. As we know very well that though so much of science has developed till today, the challenging problems that human beings are facing is we cannot create blood. Is it not? There are so many medical issues where we don't have treatment. Say, for example, if you go for kidney failure, we can't. We have to go for dialysis. And once the patient goes for dialysis, you know the life of the patient. He will not live long because we do not know the configuration of blood. During dialysis, what are the chemicals that we are going to use? We use to clean salt, and then to clean, we use sodium chloride. We will just remove sugar content, salt content, and then refill the same blood inside the human being. During that process, what actually happens is the HB will reduce. The HB will reduce and reduce and reduce. After some period, after 3 or 4 years, the patient will collapse because of reduction of HB. Why this problem? The problem is I do not know what are the contents of the blood. So, with some approximation, I take out the blood, combine with water to remove salt, combine with sodium chloride to remove sugar. Like this, it is all based on assumptions. It's all based on assumptions. So, till today, we do not have, I cannot confidently tell that, yes, this is the fluid that is used to define blood. So if a scientist can create this, they can create wonders. They can create human beings. Of course, the challenging problem once again is with our brain. Brain is still not studied. Just previous slide, previous professor spoke about AI. AI is nothing but related with understanding the functioning of our brain. Is it not? So once we come to know the configuration of blood and the functioning of brain, I think one can create a human being. These are all the challenging problems that are facing. So in that perspective, I found that instead of considering a regular Newtonian fluid, let us go for the non-Newtonian fluid, particularly the micropolar fluid. Again, in micropolar fluid, I wanted to understand what are the effects of using nanoparticles with micropolar fluid. So you must understand there are two different approaches. The first approach is, see, micropolar is the fluid which is already having particles of small size. They are suspensions. They are suspensions. Like in blood, we have RBCs, we have WBCs. They are all suspensions. That's why blood is treated as a non-Newtonian fluid. Of course, again, blood behaves differently when it is inside the body of the human being, and it behaves differently when it comes out of the body. We see clotting. When the blood is exposed to air, it clots. But when the blood is inside the body, it circulates. That is life. So the peculiar behavior of blood, we cannot really tell. See, when it is inside the body, it flows. It flows means it should match Newtonian fluid, right? But no, it has it flows like water only inside our body. But is it water? No, because it has contents like W. They are suspensions. So that's why we match blood with respect to micropolar. Even micropolar, we have suspensions. Now, what is nanofluid then? Nanofluid is also a fluid with suspensions. What type of suspensions? We have, excuse me, we have suspensions, metallic suspensions. So in blood, WBCs and RBCs are naturally occurring suspensions, whereas nanofluid, it has also suspensions, but not naturally occurring. It is the suspensions that manually we are going to add in a nanofluid. So who are working with nanofluid, I will not go in detail, the preparation of nanofluid, the properties of nanofluid. Actually, people tell that nanofluid is a new technology. No, it's not a new technology. It's a very old, way back Maxwell was the first person. We should honor him because it was his thought that instead of going for only classical fluid, why can't we go for a fluid with suspension? Of course, he failed because he was not knowing that what size of the particles he should consider. So he faced with the problem of clogging and he could not succeed in the experiments. But the original thought was from Maxwell. So with this basic information, I just go for my topic. Here I'm going to understand, and one more important point, that why I take nanoparticles, because you know very well that in recent years we have cancer treatment well advanced using nanoparticles. Cancer treatment using nanoparticles. What they are going to do is, wherever the portion of the body is affected, they remove it, and what they do is, on that part they keep gold nanoparticles so that the bad cells will not generate again. This technique is being used in cancer treatments. So not only in cancer treatment, in biomedical field, we know how important of using nanoparticles. It's been used even in many therapies. Many therapies. It's an advanced technology. Okay, so in that perspective, I thought this result may be of some use in the either in the biomedical field or even in engineering field, because it's only a modeling. So I cannot specifically tell which field it is applicable. Just I'm going to consider the geometry, do the modeling, and then give some flow and heat transfer properties and what are the here, and also rate of heat transfer, skin friction uh, modeling. Okay, so with this, I just start my talk that here I have included dissipative heat on a radiative micropolar hybrid nanofluid. Instead of considering single nanofluid, we go for different combinations of nanoparticles. A lot of work is already done on single nanofluid. I myself have published on this topic using single nanofluid, but just I wanted to know what are the benefits of using two different nanofluids. Same base fluid, but two different nanoparticles. So here for radiation effect also I have considered the normal Rosland's diffusion model is been considered, and I consider copper and titanium oxide. Of course, this model you can generalize it for any type of nanoparticles. Only we need to run the code. But to be specific, I have considered copper and titanium oxide. One is metal and one is oxide. Just this choice can be arbitrary. So whoever is interested, they can choose the respective experimental particles and then they can run the code and then they can get the result. This is a very general model. So in order to go here, as we know very well that mathematics, the limitations of mathematics, I don't want to go in detail about numerical modeling. So it's highly impossible for us to solve even a second order ordinary differential equation exact solution if the roots are complex. So mathematics will not help in the sense that exact solutions will not help. So we switch over to numerical solutions. Numerical solutions are once again approximate solutions, but better. At least we will come to know what is the structure. We cannot give you exact solutions, but we can claim that this is the type of the solution. So regarding the application of micropolar, as I have already explained, so it is a complex fluid and it has suspensions and also colloidal systems. It's useful in variety of scenarios where angular momentum. So micropolar fluid have angular momentum, internal rotation, microstructure, and it is well fit for blood flow. Once again, I repeat, 1966, you read Eddington's paper. So red blood cell rotation and internal angular momentum can be incorporated into blood flow models using micropolar fluid dynamics. Next, I have considered in particular wedge geometry because it is useful in many engineering contexts and also in aerodynamics because wedge shape is a very particular geometry where you can use both in aerodynamic and also in propulsion systems. Further, what I did is I also go for external sources of heat. It will enhance your heat transfer. You can control with the help of this heat source. You can control whether you want more energy or less energy. So that is also one of the important factor. When once we are doing modeling, I thought let me take all possible properties. So temperature fluctuations and thermal energy, this is the importance. So higher temperature differentials within the system are produced with the heat source elevation of local temperatures. So heat transmission is facilitated by this temperature. That means source is a term where I can handle it to myself apart from the natural occurring so heat changes. So let us go for the formulation. So here it's a two-dimensional micropolar fluid flow, incompressible. So I take copper and titanium nanoparticles. Geometry is defined. The angle between the wedge is pi beta and y directions. Temperatures, TW refers for the temperature at the wall. And here I'm considering in particular the free stream velocity to be, this is a very important contribution of this work. The uniform velocity I express in the form of Cx to the power of m. What is m here? Here Cx to the power of m goes for your power law. It's Falkner's scan flow. So who are interested, they can just read about this so that they will understand about the power law parameter. We define that parameter as beta divided by 2 minus beta, where beta is nothing but omega by pi, which denotes the Harty pressure gradient, and omega is the angle between the wedge. So it's a beautiful relation. Normally, most of the papers do not include this one. So this is also an important contribution of this work. So these are all the derived Navier-Stokes equation for non-Newtonian fluid. So here this represents your equation of continuity. And because of rotation, you will have two velocities, u and w. So derivation of Navier-Stokes equation again is well defined in an engine paper. So I follow that paper only. So convert in, he has given in vector form. Now what you have to do is you have to fit in for your geometry. So these are the equations. Here mu HNF refers for your viscosity of hybrid nanofluid. HNF refers for your hybrid nanofluid, the suffix. Kappa is your micropolar rotational parameter, N and W. So these are all the equations for your micropolar fluid. So who are working in fluid mechanics, they know all these equations very well. Again, your heat equation, I am considering Q, which is a source term, and radiation, which is dou QR by dou Y. Boundary conditions, because it's a boundary layer equation. So at y equals to 0, all the velocities are 0, and n is defined as dou U by dou Y. And QW is also considered as minus KHNF dou T by dou Y. And at y, as y tends to 0, naturally, velocity also tends to 0. T also tends to T infinity. So in order to define what type of radiation, normally we take Rosland's expansion. So Rosland's is obtained by using the Taylor series. So dou QR by dou Y comes to equation 7. Now, what I'm doing is, I'm doing the simulation work. Simulation in the sense that, suppose if I use only copper nanoparticle, that means only one nanoparticle, how will be the flow? And suppose if I take both copper and TiO2 combined, that means for mono nanofluid and hybrid nanofluid, I did the simulation. So the concentration, we should be very particular with the concentration of the nanoparticles. So copper, I'm taking 0.2, and TiO2 for hybrid nanofluid, I'm taking 0.05. These can be changed because after all it is a modeling, we can go for any values. So now, what are the thermophysical properties? So there are lot of relations between these. How they are going to consider these relations is they consider the experimental values and then they give the model. Say for example, mu HNF over mu F. For this problem, I'm considering that relation to be 1 upon 1 minus phi 1 to the power of 2.5, 1 minus phi 2 to the power of 2.5, which is the well-known Maxwell model. But you can see in the literature lot of relations. The relations of hybrid nanofluid with the regular fluid. This is once again, you see review papers. If you read review papers on nanofluids, you can see ample of relations. I don't know where the research is going on, because this nanofluid is, though it looks so simple outside, but it is not so, because the nanofluid relationship differs from one experiment to another experiment. So it is really very difficult for people like us who are doing modeling, which relation we have to consider. Of course, when you have experiment, yes, you can happily say that this is the relation that holds good. But modeling people, we are facing still difficulty. So I don't know whether this research is helpful or it is in air. I don't know. But this is what we have to do. We don't have any other choice. So this is the relation which I am considering for rho HNF by rho F, and also KHNF by KF. As I told, I take Tiwari-Das relationship, and I take Maxwell's. And again, here I take Tiwari-Das model. What is the meaning of Tiwari-Das model? You can see here in my basic equation, I consider mu HNF, rho HNF separately. That means, again in nanofluid, there is a lot of controversy whether we have to consider, because when we go for mathematical modeling, we should we have to define whether my fluid is homogeneous or heterogeneous. Suppose if it is homogeneous, fine. There is no any ambiguity, because all Navier-Stokes equations are homogeneous. Suppose if it is heterogeneous, what is the meaning of homogeneous and heterogeneous? As we know very well that nanofluid is prepared with the base fluid adding nanoparticles. What are those nanoparticles? Nanoparticles are solids, whereas base fluid is a fluid. So the physical properties of nanofluid and solids are completely different. The thermal conductivity itself is different. Then how we have to consider that solid and fluid are homogeneous? They argue that because we are considering the size of the nanoparticles very small, so we can assume the conductivity or properties of fluid and solid are equal. But Bunjorno questions, however small it is, but it is different. So he defines the basic equations for nanofluid in a heterogeneous model, not in this way. So there are two different research is going on. One part of the people, they use Tiwari-Das model. One part they use Bunjorno's model. But it's really sorry to say that even after 15 to 20 years of research in nanofluid, it is difficult to judge or come to the conclusion for any of the researchers which model is correct. I'm speaking about modeling. Fine. So, unsolved questions. These are all million-dollar questions. So, when we are doing modeling, we assume. So, assumptions give us a lot of space to do anything. So, assumptions are assumptions only. Anyhow, the only possibility is we have to compare our results with the experimental, then justify our result. That's the only way left for us. Fine. So this is what I wanted to highlight, that I'm using Tiwari-Das model and I'm using Maxwell's model to define my fluid. So these are all the thermophysical characteristics. The question comes about how to find the solutions of, these are all highly you can see that when we go for micropolar, it is coupled. It is coupled. So that too partial differential equation. That too two-dimensional. So you cannot imagine that you can find an exact solution for such type of equations. So what we are going to do is we have to take the help of the numerical methods. So what is the process of finding numerical solutions. There are many ways of finding this numerical solutions. So one of the method is what we are going to do is we give some transformations. I change my space of 2 dimension into 1 dimension through some transformations. So who are expertise in complex analysis, they know how to do the transformations. So what I'm going to do is this 2 dimensional, I make it into 1 dimension through a very beautiful transformation. So how we are going to do this transformation is again, it is an expertise of the researcher. So you have to keep one thing in mind, that whenever we do any transformation, that should lead with no zeros and poles. That is very important. When we do the transformation, your domain of field should be, it should not have zeros and poles. It should be analytic. The whole domain should be analytic. That care one should take. So that we cannot put it in the paper. These are all the things that we have to do behind the actual solving the procedure. These days, I wanted to mention that one of the very well-known Professor Barletta, he is from North Italy. He is doing wonderful work on this field. He is an expertise in fluid mechanics, but he is explaining, he has published very good papers that how one should check your domain of study is free from zeros and poles. Very beautiful. This is the first time I read such papers. Actually, complex analysis people, they do research separately. We fluid mechanical people, we do research separately. So, but how one should check this one is very first time I have seen in the literature that Professor Barletta started this research work. Of course, I'm also unhappy that I could not understand his paper completely. So if anybody is interested, you people can try, youngsters can try. This is a very good type of research nobody did in fluid mechanical papers. So you people try to start. It's really a very good contribution to the research society. It's a you should have very good knowledge in complex analysis, and also you should have very good control in differential equations, solving differential equations, and fluid mechanical problems. So combination of these three big knowledge is very much essential. But people are working on that. So except Barletta, I have not seen other people publishing this type of work. So even I cannot publish. So that's why I'm telling the youngsters to fetch their new work in this direction. So these are the similarity transformations that I have used. So it reduces to one dimensional, and again coupling, because I cannot escape from coupling because it's a micropolar. So you have rotations, you have angular momentum. So these are the equations. I'll not go in detail about the basic equations and all those things because the participants interest, I don't know they are from mathematics or not. Anyhow, this paper I have already published, micropolar for monofluid. You can read if you are interested. So these are the transformed boundary conditions. And here I'm going to consider mu nf by mu hnf. It goes for some 30-page computation calculation. So one should sit and do all those things. Then define all the parameters of physical interest. Physical interest like Nusselt number, then Reynolds number. You know, Reynolds is the best dimensionless number to understand the fluid flow. So the local Reynolds number, and then we are Harty pressure gradient. That's what I told. This is the major contribution of this work. So Harty pressure gradient. So in order to validate the present result, I have validated with my own paper. And of course, in my paper, I have validated with other papers. These are all the formal steps any researchers in fluid mechanics will follow. Just I'll move on to the solutions. So I think because of time, Nawaz, shall I take a little bit more time or I should wind up?
Yes, yes, please take time, no problem.
Okay, thank you. So these are all the results that we obtained. So of course, in order to understand a better way, visualization is the best model. So we visualize in the form of the graphs. Here you can see that K is a micropolar parameter. This is the important this one. So we need to understand. We need to understand that K equals to 0 goes for Newtonian fluid. That means there are no inertial material parameter. K0 goes for your pure Newtonian fluid. So that we can understand in a better way, depending on my requirement, whether I should go for Newtonian or micropolar, depending on my requirement, what type of result I want. So always whenever we are going for numerical modeling, try to include all type of parameters so that the reader will take whatever he wants. So here I have considered even Newtonian fluid also. So K equals to 0 refers for your Newtonian fluid and K 0.5 and 1 and 1.5. And one very important observation of the micropolar fluid is that when you go for material parameter K, if you go for 0.5, 1, 1.5, you see that after that there will be no variations. That means this material parameter is effective only in the range between 0 and 2, not more than that. 0 is of course Newtonian fluid. So if you take 2 and more, there is no any effect. So the effect of material parameter is not like Eckert number or like other parameters. This I'm telling in a more general way because I did micropolar fluid lot of problems. In all problems, I'm getting the similar result. I don't material parameter. If you go more than 2, there are no. That means you even if you take 3, 4, 5, 10, the profiles will not change. Even for 2 fluid flows, one my paper it is now having 238 citations. It's a basic paper. There, I'm happy to share with the participants that though it is a micropolar fluid, but I did analytical solutions. How I did is very interesting. It is coupled, and while evaluating the integrating constant, one should be wise enough. It's a different calculation. I just wanted to share with you. That's why it is having 238 citations. Everybody cite that paper. It's a very beautiful calculations. So just we'll go for the formal results. As I told, I do the results for both mono and hybrid. So blue color represents your hybrid, whereas the red color represents your mono. So you can see that when K is small, there is no much difference between mono and hybrid. But when K goes higher and higher, you observe that there is a difference in F dash for hybrid nanofluid. So hybrid do affect the primary velocity. Next, going for the Falkner scan. This you should understand a little bit physics of this one. So here you have you can go for, suppose if I take m equals to 0.2, m equals to 0.8, that means here I am considering only positive values. Here I am considering only m greater than 0. Of course, you can go for m less than 0 also. In some of the papers they have taken, but my code did not work for m less than 0. It is inbuilt code, not my in-house code. So it's a inbuilt, and also maybe because of the transformations. Because of the transformations, my code did not run for m less than. I go for only m greater than 0. So in the conclusion, I will just wind up. Then these are all the results for different concentrations. Different concentrations of your hybrid and mono nanofluids. So next we go for transverse velocity. So here you know very well that primary velocity is very important for us. Transverse velocity does not have much influence, but still in the, because it's a boundary layer, so its effects are dominant in the near the boundary. So you observe that g of eta is dominant in the boundary layer. And because it's a boundary layer concept, you can also say that your results are good, because when eta tends to infinity, you need to get a straight line. So it is there in all the graphs. This is one of the method of judging your results correct or not. Similarly, I'll just move on. Lot of results I have drawn. I'll just move on and go for the conclusions, where you can identify in particular the all the results. There I have explained in detail one by one. I have also done skin friction, Nusselt values, everything. Just conclusions. So in this research, the numerical shooting method is used to obtain the two-dimensional micropolar hybrid fluid solution and associated heat transfer over a steady incompressible through a wet surface. And BVP5C is being used. As I told, the code is validated. There's no second thought whether my solutions are correct or not. So I can validate and justify my results. So impact of micropolar fluid parameter reduces the velocity. Of course, in any, even for a Newtonian fluid also, when we go for non-Newtonian fluids, the velocity of Newtonian fluids is always highest than the non-Newtonian, because the Newtonian is a linear relationship, whereas this is a non-linear relationship. So, and not only that, micropolar, especially for here, micropolar, the polarity reduces the velocity field. Natural, no? When the particles take rotation and flow, velocity will be less, with and without rotation. So, without rotation, the velocity will be more. With rotation, naturally, velocity will be less. So, that this is the valued result. So, parameter, this is the classical result also with all the micropolar fluids. So as K increases, velocity decreases. And thermal profiles are also affected. When once the velocity is affected, naturally temperature is also affected. Especially Harty pressure gradient, M. M also affects your thermal profiles. And then volume fraction, that means how much concentration you take, the hybrid and all hybrid nanoparticles concentrations. For my study, what I did is I take copper and TiO2. You can, this in this paper I have not included, but in other papers I have included that taking, though it is a hybrid nanofluid, mathematically what we can do is, suppose if I take phi 1 equals to phi 2 equals to 0.2, that means that both copper and TiO2 are having same concentration. But it is not compulsory. You can go for giving different concentrations mathematically. Ali J. Chamka published one paper on this, how to consider in hybrid nanofluid concentrations different for different nanoparticles, copper and TiO2. So in this paper I have not included. I forgot, now I am remembering, but that I did in one of the paper recently published. So considering, but for this paper I have considered equal concentrations for both copper and TiO2. So here the temperature variations are with respect to power law parameter, then volume fraction, then radiation, of course heat source and Eckert number. Of course these are the non-dimensional parameters that occur in the energy equation. So naturally they are affecting the temperature. But which one will boost and which one will not boost is explained in the graph. So local skin friction increases with increasing material parameter and power law parameter and decreases with the volume fraction. Similarly, local Nusselt number decreases, whereas Eckert number estimates increase and increase the heat source parameter estimation. Naturally, as heat source is increased, the Nusselt also increases. So we did, as I told, we did the comparative analysis between mono and hybrid. Several properties of radiative laminar boundary fluids are also there. You can continue your further studies. Here I have considered only micropolar, but you can also consider different nanoparticles, especially ferro. Ferro is very much interesting. You can further continue this work using ferro nanoparticles. As I told, I have published for mono nanofluid in my profile. So you can just put my name, JC Umavathi, Google Scholar. You will get all my publications. So with this, I wind up my talk.